If you've ever needed to display a long list of items in UI Toolkit, you've probably used a ScrollView. But what happens when you add 1,000 items to scroll through? If your UI starts to lag, it's time to switch to a ListView. It looks similar, but it's built to handle large data-driven collections. Let's take a look at how it works. ListViews are similar to ScrollViews. If you haven't seen the video on ScrollViews yet, you'll find a link in the description. A ScrollView is just a container. You add child elements and each one becomes part of the visual tree. Add 500 items, you get 500 visuals. Simple, but potentially expensive. A ListView works differently. It's built for large datasets. It only creates enough row elements to fill the visible viewport. As you scroll, those rows are reused and rebound to the new data. So even with thousands of items, you might only have a dozen elements active at once, and that's the key difference between the two. This behavior is called virtualization. Instead of rendering everything, ListView renders only what you can see. Then it recycles those visuals as needed. Rows don't belong to specific items, they're just temporary containers that display whatever data is currently visible. Once you understand that, everything else about ListViews should start to make sense. Setting up a ListView takes a few more steps than a ScrollView, but it follows a clear pattern with 4 main parts. Let's walk through each one. Here's a minimal example of how to set up a ListView in code. This UI will display a simple list of integers. We'll call it makeItems, and for this example, it's our data source. The ListView itself is already defined in UXML, so we'll just get a reference to it. Then we use a helper method, configure ListView, to connect everything together. First, we assign the ListView's item source to makeItems. This is your data. In this case, it's just that list of integers. The ListView reads from this collection to determine how many items exist and what it should display. It doesn't generate data, it simply reflects what's already in the list. Next, we define makeItem. This function creates the visual elements for each row. In this simple example, it just returns a label. This is the row structure without any data. And because the rows are reused, this function only runs a few times, just enough to fill the viewport. Then we define bindItem. This is where the data gets applied. The bindItem callback connects each row's visual element with an item from your data source. It receives 2 things, the row element and the index of the item to display. Using that index, you look up the data and then update the UI. In this case, we cast the element to a label and then set its text using a formatted string from our data list. And remember, because rows are reused, this function runs repeatedly as you scroll. So whatever logic is in here needs to fully update the visual state of the row every time it runs. Finally, we set fixed item height. Let's say 32 pixels. This tells the ListView that every row has the same height, and that allows it to calculate layout more efficiently and improve scrolling performance. We also set the virtualization method to fixed height so it can take full advantage of that optimization, and we disable selection using selection type since this example is display only. After setting everything up, we call ListView's rebuild method. This refreshes the ListView and applies the new configuration. So in just a few lines of code, item source provides the data, makeItem creates the row structure, bindItem fills it with content, and fixed item height improves performance. And then finally, rebuild applies the setup. And that's the foundation of every ListView. Let's take a look at what happens during scrolling. We have a stats component in our demo that logs the callbacks from the ListView, and this will help you understand what's happening as we scroll. Notice how makeItem runs only a few times, but bindItem runs repeatedly, and that's because the rows are reused. Scrolling doesn't create new visuals, it just reassigns the existing ones. A ListView is built on top of a ScrollView. It uses the same scrolling system, but adds virtualization and data binding. If you open a ListView in UI Builder and expand it in the hierarchy, you can actually see the internal ScrollView as part of its structure. So the same rules still apply. Scrolling only works when the list view is bounded and the content needs to exceed the visible area. If the scrolling isn't working, check the usual things. Does the list view have a fixed or constrained height? Are parent containers expanding to fit the content? Always make sure that the list view is properly bounded and the content exceeds the viewport so you can scroll. Here's the most important pitfall when working with ListView. Rows are recycled. The same visual element gets reused for different items as you scroll. So UI state doesn't belong to the row, it belongs to your data. On the left, this example ignores that. If you toggle a row and then scroll, that state is lost or shows up on a different item. And that's because the change only lives in the UI, not in the data. On the right, we fix this by storing state in the data. If you check the toggle items and scroll up and back, the check state persists. Let's take a look at how this is set up in the script. This uses the same ListView setup we covered earlier. We still have a data source, a makeItem, and a bindItem. But now we're adding one key piece, writing changes back to the data. We have a simple data model, a list of toggle items, each with a name and an enabled state. The ListView reads from this list, and everything stays in sync through the two methods, makeItem and bindItem. Now we can break it into two parts: what happens when the user clicks, and how each row gets set up correctly. In makeItem, we create the row and register a callback on the toggle. When the user changes the state of the toggle, the callback runs, we update the visuals, and right away the UI responds. Then we look up which item this row represents. That index is stored in toggle user data. If it's valid, we write the new value back to the data. And that's it. The user changes the toggle, we update the data. And now the second part, how the row knows which item it represents. That happens in bindItem. This runs every time a row is reused. We grab the toggle and label, and then get the item from the current index. We update the label text, and then we store the index in toggle user data. And that's what the callback uses later. Next, we set the toggle value from the data. We use set value without notify, so it doesn't trigger the callback again. And finally, we update the row visuals. So the full flow is simple. The user changes the toggle, we update the data. The row gets reused, and then bindItem restores the UI from that data. So now you've seen how ListViews work and how to set them up. Use a ListView for large data sets or when performance matters. Use a ScrollView for small or static content. Check the link in the description to download the QuizU demo project and try it yourself. There's also a demo for a related control, a TreeView. TreeViews are similar to ListViews, but they add support for hierarchical data. And that means you can organize items into parent and child relationships with expandable and collapsible nodes. They use the same core pattern, data binding and element reuse, just applied to nested structures. If you want to learn more about ListViews and TreeViews in UI Toolkit, see the official documentation. Thanks for watching.